Now, I want to just now analyze T, okay, T. So, let T belong to the linear operators from, T is a linear operator from V to W, okay. And pick V from V. Since it belongs to V, can I express in terms of its basis? Yes, I mean that is a definition. So V is equal to C1 times E1 plus C2 times E2, Cn times En, right, for some C1 and C2, C3. Okay. Okay. Now, T of V is T of summation of Ci Ei. Okay. Because it's linear, I can use the two properties. Therefore, I'm going to get summation of Ci T of Ei, right, I equals 1 to N. Okay. Now, where is T of Ei? What is T of Ei? It's a vector in which space? W. So, now I can express that as what? A linear combination of what? F2s, right? So, I can write something like basically summation of I equals 1 to N Ci and summation of j equals 1 to m, okay, T ij, okay, what would it be? Fi, okay. So, where Tij is basically each T of Ei can be expressed as a linear combination of Fi's. So, I can do that, okay. Now, if you prefer, you may want to expand this thing. I'll do that in a second anyway. But on the other hand, what is T of V? T of V is also a vector in where? W. So, again I can express that as a linear combination of Fi's, okay, some other linear combination, I do not know what that is. So, j equals 1 to m, let us say di Fi. Any questions? Did I make any mistake? Okay. So far so good. What I am going to do now is basically equate these two, okay. So hence, summation of j equals 1 to m di Fi is equal to summation of I equals 1 to n, and I hope you won't object. I am going to basically please make this correction. J is everywhere as far as F's are concerned, okay. Okay. So what I did is here I just brought in Ci into this thing, I do not think it is going to matter. Now, can I interchange I and j in the summation? Can I interchange those two summations? So if you have two integrals, you can always interchange them as long as both the limits are constants, right? Only when basically if I had something like j equals 1 to 2i or something like that, then I have to be careful. Otherwise, I can certainly interchange. Both are sort of going from constants to constants. It's just like your double integral interchanging x and y. So therefore, I can do this. okay? And in fact, I want to put parenthesis here. Of course, the outcome is going to be dependent on I, but then it won't be dependent on, the quantity in the parenthesis is not going to be dependent on I because we are sort of summing over I, okay? Huh? Sorry? Thank you. Okay. So now with all this, okay, and we'll again go through this thing. So this basically, all this implies summation of j equals 1 to m, summation of I equals 1 to n, Tij Cj minus Dj Fj is equal to 0. Okay? So, do you see any mistake or possible? Any mistakes are made? Oh yeah, sorry. Okay. Is it okay? Yeah. Okay. Now, what can I say now in terms of basically the thing in the parenthesis in that equation? There are, of course, how many of such things are there in the parenthesis? When you expand the summation, there are m of them. Okay? So there are m coefficients, so to speak. Can I claim something about them? 0. And why? Because Fy's, Fj's are all independent, right? So since Fj's are independent, how do we know they are independent? Of course, they are bases. That's our assumption. We basically conclude summation of I equals 1 to n Tij Ci is equal to Dj for all j equals 1 to m. Okay? Okay? So that's the conclusion that we get from independence. Now I'm going to write this slightly differently. Okay? I'm going to write each one of these things in a format that is much easier. So I'm going to write d1, d2, dm. Okay? And similarly here I'm going to write c1, c2, cn. So what do you think here? What should be the first element? T11. Yes, that's obvious. Whatever you do, it's going to be T11. What's the element going to be next to it? T12, right? Are you sure? T21, okay? See, this is multiplying here, so look at this. I should be the same, okay? So it should be T21 and so on, and then Tn1, and then T12, T22, and Tn2, and similarly Tnm, and then T1m. Okay? So anyway, okay. Now, here is a question for you, right? Let's see what we have done. Let's summarize what we tried to do here. We started with two finite dimensional spaces. Did we say anything about those finite dimensional spaces? Are they function spaces or the vector space, regular vector spaces? Nothing like that, right? All I assumed is simply they are finite dimensional vector spaces. But because of that assumption, I can immediately say there are two bases, okay? And these E1s and E1s and F1s, they are something, we don't know what they are. But what I have done with all the linearity that I have here is finally wrote an equation in terms of bunch of numbers, right? You have an equation in terms of bunch of numbers in a matrix format and two vectors. Okay, what are C1s and D1s? They are nothing but the coordinates with respect to that basis, right? So in fact, you can see there is a one-to-one correspondence between this matrix and the T. So every linear map T can be written as this kind of matrix, and every matrix can be sort of thought of as the linear map T, as long as the same basis is picked. Every time we have to restrict ourselves. But then this gives us ability, now instead of talking abstractly that this is a T is a linear map on two abstract spaces, we can forget about the abstract stuff and then just focus on matrices, right? So the rest of the semester we will focus a lot on matrices, of course, but once in a while we will come to abstract spaces simply because it becomes easier to deal with abstract spaces to introduce certain concepts, not because it's fun to do it, but it's actually easier to write some of those things down. But from a computation point of view, if we know how to compute matrices, we can pretty much do all kinds of vector spaces. That's the point of this thing. All kinds of finite dimensional vector spaces. If they are infinite dimensional, this is not going to hold. Just extend your imagination. If things were infinite dimensional, what would happen is you will end up with matrices that are of infinite dimension, either this way, or both ways. And there, by the way, there is mathematics on those kinds of matrices also, but we are not going to talk about them. It's far too complicated. Okay? Infinity is always a strange thing to handle.